this video, I'm going to talk about our paper, Deep Learning Models for Global Coordinate Transformations that Linearize PDEs. This appeared in the European Journal of Applied Mathematics in a special issue on connections between deep learning and PDEs. So I'm Craig Jin. This is joint work that I did with Bethany Lusch, Steve Brunton, and Nathan KUTZ. All right, so let's start with what's the goal of this work? What we wanted to do is we wanted to create a method that we could use to discover coordinate transformations that linearize PDEs. So sort of the general outline of what we want our method to do is, let's say we start with some function u that's governed by a nonlinear PDE. What we want is some coordinate transformation from u to v, where this new function v is governed by a linear PDE. So we wanted to have linear dynamics for v. So why do we want a linear PDE? Well, there are already many well-established methods that work for linear PDEs. So as some examples, we're really good at doing things like estimation, control, and uncertainty quantification in the context of linear systems. All right, so this allows us to do all those kinds of things. And in particular, we also often for linear PDEs have things like exact solutions, or even if we can't write out the exact solution, we can do an eigenfunction expansion and then easily evolve the system forward in time. So when we have this linear PDE, we can easily march forward in time from time t to t plus delta t. And then if our coordinate transformation is actually invertible, well, then we can invert the transformation and we have our solution u to the nonlinear PDE at some time in the future. Okay, so we want to try to emulate this procedure here. So one question that might come to mind is, how do we know if there is a coordinate transformation? If we have some nonlinear PDE, how do we know whether you can linearize it with some transformation? The mathematical theory that's going to help us here is Koopman theory. So let me just give a very brief introduction to Koopman theory. So let's say we have some discrete time dynamical system. So u here is our state variable and f is the evolution operator. So in our case, this is just going to be the discretization to some PDE. All right, so for a discrete time dynamical system, the Koopman operator, it acts not on the state variable itself, but on the space of observables or functions of the state variable. And the definition of the Koopman operator, it's just a composition operator. So the Koopman operator applied to this observable is just the observable composed with f, which is the original evolution operator. Okay, and importantly for us, the Koopman operator is linear. Okay, so that's going to allow us to linearize our system. And if you take a look at what happens on some trajectory of your dynamical system, the Koopman operator applied to g of uk. By definition, it's just composition again. And then if you look at what is f of uk, well, that's just uk plus 1. Okay? So if we just do a little bit of rewriting our terminology here, we just define this vk as g of uk. Well, then what we get in the end is that vk plus 1 is just the Koopman operator applied to vk. All right, so compare the bottom here to the top. And what do you see? We went from a potentially nonlinear dynamical system to a linear one. Okay, so this is the theoretical framework that we're working from. So when we get to the practical, the unfortunate thing is we generally don't know how to do this, right? How to find what the Koopman operator looks like. There are actually just really two examples that we have where we know how to linearize some PDE. So one is going to be the Kohl-Hopf transformation. So the Kohl-Hopf transformation takes the Burger's equation and linearizes it. You get the heat equation. And then the other really important linearizing transformation that we know is the inverse scattering transform, which linearizes a class of completely integrable PDEs. So things like KdV and nonlinear Schrodinger, Klein-Gordon. So we have that example as well. So what we're going to do to sort of develop our methodology is start with one of these examples where we already know how to linearize and see if we can sort of model things after that. So as our example, we're going to look at Burger's equation. Okay, so let's say we have u, which satisfies the viscous Burger's equation. If you take the Kohl-Hopf transformation, we're going to get v, and v satisfies the heat equation. Okay, and well, that's great because we know all kinds of things about the heat equation. We know many of the properties of the heat equation. In particular, we know eigenvalues, we know eigenfunctions. We can write down exact solutions, things like that. So one thing I want to point out is that you can diagonalize the heat equation using the Fourier transform. And once it's diagonalized, then you can evolve forward in time. It's just taking these eigenfunctions and multiplying by eigenvalues, right? So we're gonna talk about that in a few minutes. But we go from this nonlinear equation, viscous burgers, to a linear equation, the heat equation. And then if we want, we can evolve forward in time, and then we can invert our transformation to get back to U. Okay, so we are going to try to do this with neural networks. So we're going to use deep learning to try to learn the coordinate transformation and learn the dynamics in this linear space. All right, so up top here we have some solution to Burger's equation. So the initial condition we highlighted in blue, and then one time step into the future is in yellow. So the way our neural network is going to work is that the input to the neural network is just a discretized version of the initial condition. So you take the initial condition, you discretize, and you feed that into the network. And then we're going to use an autoencoder type architecture. So here in yellow we have the encoder, and then over there in pink is the decoder. All right, and the encoder is going to do our linearizing transformation. Then once we're in this linear space, our dynamics are going to be linear. So to march forward in time, that's the middle of the network here, we're just going to have some linear operator. So since we're in a discrete space, this is just a matrix. Matrix multiplication is how we move forward in time. And then once we move forward, we can then decode, which is inverting this linearizing transformation. And actually, there's a little bit more to it because we take our autoencoder and we split it into two parts. So we have an outer autoencoder and an inner autoencoder. So here, if we look at the encoder, this part here is what we refer to as the outer encoder. We have some neural network, but this is the part of the network that does the linearizing transformation. Okay, I guess one important thing that I want to point out is that we used a residual neural network architecture here. So we have a skip connection where we just take the identity times the input and add it to the output. Okay, so why do we do that? Well, it's sort of inspired by physics, where we can think of a transformation as being a near identity transformation. The identity plus some residual term. So we're just learning the residual with some nonlinear neural network. This may seem trivial, but it actually is pretty important to the success of the network because even though the identity is kind of a trivial operation, learning the identity with a nonlinear neural network is not so easy to do. So we sort of hard code that in there with the skip connection. And again, this outer encoder does the linearizing transformation. What about the inner encoder? What's its purpose? It sort of has two purposes. One is to do dimensionality reduction. If you want a reduced order model of your system, then we can sort of squeeze down to a lower dimension than our input. And then the other thing is that we can, if we choose, have our evolution operator, or this matrix K, be diagonal. And in that case, this inner encoder is going to do some diagonalization. So we actually have this inner encoder it's a linear transformation. So we're having some linear dimensionality reduction and possibly diagonalization after we've done the linearizing transformation. Okay, and then for the decoder, we have the analogous thing. It's just sort of inverting those two operations. All right, so if you want to think back to our Burger's equation example, you can think of the outer encoder as doing something like a Kohl-Hoff, as well as the outer decoder, and then this inner encoder does something like a Fourier transform to diagonalize, and then maybe throwing away some Fourier modes if we want to do dimensionality reduction. Okay, and the same for the decoder on the far side. All right, so what if we want to do multi-step prediction? We don't just want to predict one step into the future, but we maybe want to go further out in time. Well, you could just take everything and feed it through the entire network multiple times, but that's not how we want to do things. What we want is for our network to be able to just encode things once, just do the linearizing transformation once, and then we'll step forward multiple times in this linear space, in our latent space in the middle here, and then we'll decode once on the far side. So this is how we do multi-step prediction. So if you want to use the network for prediction, you can feed it just the initial condition, and then it will predict all the rest by just doing one step into the future and 2 steps and 3 steps. Okay, so you only need to give it an initial condition, and we can step forward as many times as we want. Okay, so what are the loss functions we're going to use to train our network? Our loss function is actually the sum of 5 different loss functions. So the first 3 are unsupervised loss functions. We have an encoder loss function. So if you just feed your data through the autoencoder itself without doing any sort of evolution in the middle here, then we want our output to be the same as our input, right? We want our encoder and decoder to be inverses. So we have an autoencoder loss function for that. We also want the outer encoder and decoder to be inverses as well as the inner encoder and decoder. So we have an outer autoencoder loss function and an inner autoencoder loss function. We have a prediction loss function. This just means if we do prediction with our network, we want it to match up with the actual solution to the PDE. All right, and then the last one we call a linearity loss function. And this just says if we take our solution at some time, so UK, and we encode it and then march forward in time, p steps, that should be the same as if we took our solution p steps into the future and just encoded it. All right, so these are our 5 loss functions. One thing I want to point out is that there is some redundancy in these loss functions, right? Some of them imply the others automatically, but what we found is that by having some reinforcing loss functions that we got much better results in the end. Okay, so our goal, remember, is to take a nonlinear PDE and linearize it. But to actually just get us started and sort of see how these networks behave, we started with an equation that's already linear, so meaning the heat equation. Okay, so we wanted to see how does this methodology work with the heat equation. But because it's already linear, we actually don't need linearizing transformations. We don't really need this outer encoder or the outer decoder. We really are just looking at the middle of the network. All right, so we're just going to use like the inner parts of the network and see what it does with the heat equation. So our full network actually just looks like this. So we have our inputs, and then we have this is like our inner encoder, which is going to like play the role of like a discrete Fourier transform. Because remember, for the heat equation, we can diagonalize with the Fourier transform, and then also that's actually like the best way that we could do dimensionality reduction for the heat equation. Right? The heat equation takes high frequency stuff and damps it out really quickly. So we can do discrete Fourier transform, and if we do reduced dimensionality here, then it should just keep sort of the lowest frequency stuff. Okay, and then we have because we're diagonalizing, we can have just a diagonal matrix that moves us forward in time. And then on the back side, we want something that's like similar to an inverse discrete Fourier transform. All right, so we have a network like this with just the inner part of the net, our full architecture, and we're training on data from the heat equation. All right, so if you look at what our training data actually looks like, we had to discretize. We used 128 equally spaced points, and we had 50 equally spaced steps in time. And for our data, we actually chose all white noise initial conditions, just randomly generated white noise as the initial conditions to the heat equation. And we solved 50 steps forward in time, and that was our training data. All right, so one thing that we should be able to do with this network is pick out what are the eigenvalues and the eigenfunctions for the network. Right, our network is sort of diagonalizing and reducing dimensionality here. So what we did plotted here is the actual eigenvalues of the heat equation. So if we've taken the eigenvalues and taken a negative logarithm and divided by our time step, then actually what we should get is an eigenvalue at 0, and then 2 of them at 1 squared, 2 of them at 2 squared, 2 of them at 3 squared, 4 squared, and so on. Right, all the integers squared. And that's actually what we get. We get really good agreement between the network and our exact values for the eigenvalues. But on top of that, we also get really good agreement in terms of the eigenfunctions. So if you have an eigenvalue that's 1 squared, then you should get sines or cosines that have a frequency of 1, which is what we get here. Or if we have an eigenvalue of 3 squared, we should get sines and cosines that have a frequency of 3, which we get. Same thing as we move up the ladder. So yeah, we got really good agreement. Our network actually does a really good job of being able to find the right dimensionality reduction that retains the most information and picks out the right diagonalization of the system. So this is great. So this is good performance for sort of the middle part of our network. One thing I want to point out is if you look at the eigenfunctions, you do see like different scales, like different amplitudes here. And that's because the Fourier transform is actually not a unique transformation for diagonalizing the heat equation. You could also scale each Fourier mode by any arbitrary constant that you want, as long as when you're inverting, you undo the scaling. All right, so it's not really a unique transformation, and that's what we see with our network. When we actually train the network, if we take some input to our network and do the encoding, we get something really different than if we just take that input and we do a discrete Fourier transform. And that's because you can take all of these Fourier modes and scale them by arbitrary amounts. All right, so one really important thing here is that we had a fully linear network when our actual PDE was linear, because if you have a linear system or a linear network, then if you just have the right eigenvalues and eigenfunctions, then you can bootstrap everything from there, right? Everything has, you can then expand in terms of the eigenfunctions and with those eigenvalues, and you'll get good results for sort of any type of initial condition you want by doing this expansion. So if you have a nonlinear network, then that's not really true. So here is an example where we have from our training data some exact solution to the heat equation with this white noise initial condition. Here's what our linear network says in this case. So you'll notice that because we did some dimensionality reduction, the initial condition is actually looks different than the exact solution. So what I'm showing here is like the initial condition for the linear network is actually just if you feed it through the autoencoder without moving forward in time. So looking at the initial conditions gives you like some sense of what the autoencoder does. And then if you look further out in the trajectory, that shows you how well we capture the dynamics. Okay, and well, if you look especially at like later times, the linear network gives you something very similar to the exact solution. But if you trained a nonlinear neural network, which we did on the far side there, you also get pretty good behavior when looking at the training data. But when we move to test data that has a different type of initial condition than what we trained on, the linear network still performs very well. So here we fed in a sine wave and solve the heat equation. A linear network can reproduce this faithfully, but if you look at the nonlinear network, not so good. So a lot of jagged edges, wrong amplitudes, things like that. And that just is because for a nonlinear network, you're not going to do a good job of generalizing outside of the training data that it's seen. Whereas for a linear network, you have superposition, so things sort of hold outside of that range. Okay, so now let's move to what we actually really want to do, which is linearize a nonlinear PDE. So let's go back to our example of Berger's equation, which we have written here. And well, now we need our full network architecture to be able to linearize Berger's equation, right? So we're adding on now the outer encoder and decoder so that we can actually do this linearizing transformation. I guess one thing we haven't addressed is what should the network architecture be for the outer encoder and then equivalently the outer decoder on the far side? Well, that's actually something that's sort of flexible in the method. You can choose whatever neural network architecture that you want. Different things are going to work, and you can try to find what's the right choice for your specific PDE that you're using the method for. So for Berger's equation, we started with something really simple. We just chose a really simple feed-forward, fully connected neural network for the outer encoder. So the network architecture we chose, just several fully connected layers, I guess 4 hidden layers. So our skip connection goes from this input here to the output over there of the outer encoder. All right, so something really simple, and even with this, something simple, we were able to get good results in trying to find this linearizing transformation. Okay, so our training data for Berger's equation, well, we numerically solved it a bunch of times. We chose a discretization of 128 spatial points and 51 time steps. For this, we chose more of a variety of initial conditions. We chose initial conditions of 3 different types. So again, just like heat equation, we chose some randomly generated white noise. We also had some sine wave initial conditions. We chose sine waves of different amplitudes and frequencies, which were also randomly selected. And then we also had square waves, so square waves with different widths and different heights. And actually, one thing that we found to be really important is choosing a variety of initial conditions in your data set. So to sort of, I guess, illustrate that, we actually created 3 data sets. So the first data set, which in the next figure is going to be called data 1. So data set number 1 had only white noise initial conditions. All right, so all of the initial conditions are white noise in data set 1. Data set 2, we added in a second type. So data set 2 has white noise and sine waves. And then data set 3 is the most sort of robust data set, the thing with the most different types of initial conditions. The most variety has all 3 types. All right, so data set 1 has 1 type of initial condition, data set 2 has 2 types, data set 3, 3 types. Okay, so we wanted to see how our network would perform with these 3 different data sets. We trained networks that had, I guess in one case, no dimensionality reduction. So our linear space was the full dimensionality of the system, 128. And then we also trained a network where we did do some reduced dimensionality. So the dimensionality of our linear space in that case is 21, a rank 21 system. So here we show the results. So the average prediction loss on white noise initial conditions, sine waves, and square waves. Those are the 3 types that were in our training data. But we also evaluated on some things that were not in our training data, in particular Gaussians and triangle waves. All right, and we did it for 3 different data sets, the ones that we just talked about, and for the full width network and a reduced order system. The results are similar in both cases, so we'll just point at this first one, the full width network, and see what the conclusion should be. So first of all, what if we train just on white noise? That's sort of the diamond shape here. Well, you can see we get really good loss on white noise itself, but then when we try to do some extrapolation to sine waves, square waves, Gaussians, or triangle waves, the results are much worse, like orders of magnitude higher than the results on the training data. Okay, but what if we train on data set 2, which are the stars here? So again, we do very well on the white noise, actually not quite as well as if we trained on only white noise, because the network had to learn how to do white noise and sine waves. But you can see we now do much better on sine waves, which is expected, but still not great on the other types of data, right? The different types of initial conditions that the data hadn't seen. But now look at what happens when we get to data set number 3. Okay, so this was trained on white noise, sine waves, and square waves. So it's not at all surprising that it does well on those 3. But look at the sort of the initial conditions that are not part of the training data. So this data set 3 actually does better on Gaussians than the ones that were trained on less diverse data sets, and it does better on triangle waves than the ones that were not trained on as diverse of data sets. And it's actually much more extreme in the reduced order case, right? Like look at the difference between this diverse data set versus the less diverse ones, and same thing over here. So having a diverse set of initial conditions that you're training on is going to be important to having your network generalized to different types of initial conditions. Okay, so how did our network actually do with prediction? Well, here's a few examples to just give you a visual of how the network is doing. So here on the left column, we have exact solutions to Berger's equation. And on the right are the network predictions. So again, if you look at like the initial condition, which is shown in blue, what's shown in blue for the network is actually what happens if you feed it through the autoencoder. So looking, comparing blue to blue gives you a sense of how well the autoencoder is doing. But then if you look at the rest of the time steps, that gives you an idea of how well we're doing at predicting. How well can we replicate the dynamics of Berger's equation? I guess what you see here is actually we have a really faithful representation of Berger's equation. The network predictions are very similar to the exact solution. One thing that I want to point out is that if you look at the top 3 examples, this is a white noise initial condition, a sine wave, and a square wave, which are the types that are in the training data. These are not actually training data examples. These are from a withheld test set, but they're of the type of the training data. But then at the bottom 2 here, we have a Gaussian and a triangle wave, which are different from our training data. And you can see that actually the results for those 2 are look just as good as some of the other examples that are in the training data. So you can do quite well even on initial conditions that were not in your training data, as long as your training data was sufficiently diverse. All right, so I guess one question you might ask is, did we actually learn the Kohl-Hopf when we trained this network on Berger's equation? And the answer is no. So just like when we did the heat equation, it didn't exactly give us the Fourier transform. There was some wiggle room to sort of scale the Fourier modes. Here, if you look at some just sample network input, the actual Kohl-Hopf transformation is going to give the yellow here, and what our outer encoder is actually doing is given in blue. So you can see that the actual encoder is doing something very different than the Kohl-Hopf, but still, based on what you've seen in the last slide, did a good job capturing the dynamics. So same thing in the bottom example. The Kohlhoff is something very different than what the actual outer encoder is giving us. So we might also want to see, like, how does our network perform when we have different widths for that, latent space. So when we, reduce the dimensionality of the system. So here's a plot of, the possible ranks of the system, or how wide is that, that linear space versus our validation loss. And on a log-log scale, you can see sort of this, linearly decreasing. So as we have, more dimensionality, we can, capture more of the full system, just like you'd expect. And then next, I just wanted to show the importance of actually having really good data and the right network architecture. So here in the top left is our exact solution. And our very best network that we trained is the results are given here. So here we use that residual neural network architecture with that skip connection. And also you use data set 3, which was the most diverse data set. And you can see the mean squared error of relative mean squared error is 9 times 10 to the minus 4. And then on the bottom row, we have some networks that were trained with slightly less than ideal conditions. So if you look, I guess here on the bottom right, this was trained on the diverse data set, but without that skip connection, without the residual neural network architecture, which actually adds no new parameters to the system. So it's a fair comparison. And you can see we lose almost an order of magnitude in performance. And then what if we choose the right network architecture? So this is going back to using a residual neural network, but just not using a diverse enough data set. You can see we lose actually another order of magnitude in our performance. So it is important to both have the right data set with diverse enough initial conditions and the right neural network architecture. OK, so if we stopped there, then we haven't really actually done that much. What we did is we found a linearizing transformation for Berger's equation where we already know one. Right? So what we wanted to do is now use our methodology on a system where we don't know how to already linearize the system. So we chose the Kuramoto-Shivasinsky equation. And this is a PDE that's nonlinear. And there is no known linearizing transformation. But we want to try to use our neural network architecture and our methodology to linearize this system. So again, this is the overall network architecture. One thing that I mentioned earlier is that if you look at the outer encoder and the outer decoder, the actual network architecture is flexible. You can choose different things and try to get the best performance you can on your particular system. So to show the flexibility in the system, we chose a different network architecture for the outer encoder and decoder. We could have chosen it exactly the same as Berger's, and actually the results are still pretty good. But instead, we chose something that actually gave slightly better results. We chose a convolutional neural network architecture for those parts of the network. So we have alternating convolutional layers and average pooling layers. Okay. So how did our network do working on this system that we don't already know how to linearize? Well, actually, the predictions are pretty good. So the results I'm showing here are actually for a reduced order model. So in this case, we had rank 21 as the width of those sort of our linear space. So that actually explains why if you take a white noise initial condition and then feed it through the audio encoder, we don't get something that looks like white noise still, because you have to reduce the dimensionality. Although for things like a sine wave, our autoencoder actually can sort of faithfully reproduce that. But you do see some inconsistencies here between the inputs or the initial conditions and what you get when you feed them through the autoencoder. That's not about the actual system itself. It's more about the reduction in dimensionality. But then if you look at the dynamics, right, what you get further on down in your trajectory, we actually have, again, a really faithful representation of the dynamics, right, if you compare sort of what we get from the network versus the exact solution. And that holds for things that are similar to the training data, but also, again, on things like Gaussians and triangle waves, which were not at all seen in the training data. Right? So even though we didn't train on Gaussians, if you look at sort of the later time behavior, you still get a faithful qualitative representation of the dynamics of KS. All right. One more thing that I wanted to talk about here. So when we train our network, we do have to make a choice of our time step, delta t. Right? So the evolution operator, that matrix K, it's like evolves some certain fixed delta t in time. So we could train our network on different time steps, different delta t's. And I guess really all that should change by changing the delta t is the operator k, right? That matrix that we're multiplying by to evolve forward in time. What doesn't need to change when you change your delta t is your linearizing transformation, right? That does not depend on the time step. And so actually when we trained for the KS equation, we sort of harnessed that information to try to get some better results. So first of all, one thing that is really not surprising is that when you try to learn a smaller time step, we get better results, like a smaller loss when we have a short time step, as opposed to trying to learn large time steps. If you want to step further in time, you're going to have greater error. So that's not surprising. But what I want to point out is that these results here, we're using some transfer learning. So what we did is we took our data with a small time step, and we trained a neural network to learn a linearization of KS, of the Kuramoto-Shivasinsky Equation. And these are the results we got. But then we tried to train on data with a larger time step, but we initialized with the autoencoder from the shorter time step. So using the initialization from the shorter time step, we could do much better on larger time steps. So these results are actually using that transfer learning, which we could also do for Berger's equation or whatever equation you're using. And actually sometimes the gains we got in loss were astronomical, more than 100% better. Sometimes for longer time steps, our network wouldn't really even converge to anything useful without doing this transfer learning. So I think there are a lot of other techniques you could sort of build into this. It's a flexible sort of machinery or architecture to try to do this linearization. But this is just one example of some machine learning, a common machine learning technique that you can use to get better results. All right, so concluding, what we did is we developed a deep autoencoder architecture that learns transformations to linearize PDEs. Some highlights of the method, important things. It's completely data-driven. You don't have to know what the equations are to be able to train a network. So you can do this on systems where we don't have any equations. We had an interpretable neural network, so we can say this part is doing linearization, this part is marching us forward in time, things like that. The transformations we're learning are global. So it's not just for one initial condition. It's for any initial condition. That's what we're trying to do, is learn a transformation that works for any initial condition or function. And also, we have an architecture or a methodology that's generalizable to different types of systems. Different PDEs, you can use this methodology. One thing that I want to point out is that we actually had many failed attempts in trying to train these networks. And really, to get success, we needed to have certain ingredients just right. So I wanted to sort of highlight those things to show what's important in trying to get good results when you're doing your neural network training. So first of all, we needed judiciously chosen data. So we talked about that a little bit. You need a diversity of initial conditions to then have your network be able to handle new things that it hasn't seen before. So yeah, ideally you want to have many different types of initial conditions to have a more global transformation. We needed the appropriate neural network architecture, so we harnessed autoencoders to be able to find invertible transformations. And then we also took advantage of ResNet architectures, having these skip connections that sort of hard code in the identity transformation. And then we also needed a really strategically chosen loss function that sort of enforce different conditions that are desirable for our network. All right, so there are many more details that you can find in our paper, so I'd encourage you to go take a look. Also, we have code up on GitHub that you can use if you're interested in trying to use our methodology for some problem that you're working on. And there's actually another video where I walk through the code and make it easy for you to see how to use it. So yeah, take a look at that video if you're interested in learning how to run the code. And if you just want more details on our network architecture, all the details that we use for training, I'd encourage you to check out the paper.